Hi, today we move on to talking about polynomial vector spaces. Okay, and really, these are the first different kind of vector spaces that one should really learn about other than Rn, right? So we're very used to Rn, right? That's the vector space consisting just of column vectors with n entries in R, even Cn, which basically behaves the same way. That's like the first example of a vector space that we learn about in 308 for good reason. It's probably like the most useful one. But we said that in this class we'll learn about some other kinds of vector spaces. So we did see that if you look at the set of all m by n matrices, right? So let me not write everything here. We did talk about how these form a vector space because you can add them, you can scalar multiply them, and there's a zero matrix. But to be honest, most of the time when you think about matrices, you think about them as representing linear transformations between vector spaces. They do form a vector space, the m by n matrices, but usually you don't think of them as vectors. You usually think of them as functions. The next one that we're going to learn about, which is this week, the next few lectures, is we'll learn about Rx. This will be the vector space of polynomials, of univariate polynomials. I'll define these things in a sec. And then we'll also learn about a bunch of smaller vector spaces, Rx sub d, where d is a natural number. Let's say greater than or equal to 1, probably. Yeah. Okay, so these are, like I said, the second ones that you should learn about because they are genuinely very useful. There are lots of times when you want to think about polynomials as vectors in a vector space because you want to do linear algebra with polynomials. Okay, so the running example for this first part lecture is going to be, you could pick any polynomial you want, but let's just pick the polynomial, it's called p of x. It'll be x to the fifth minus 20x to the fourth plus 8x squared minus 10. Right, and we're used to looking at things like this from calculus. It's a polynomial in a single variable x, and that's what the univariate refers to. Right, so univariate here means in one variable, and we'll most of the time use the letter x, but of course the name of the variable doesn't really matter. Right, it could have r brackets y, and it's basically the same thing. Okay, so let me now just define a bunch of terms that we'll use when dealing with polynomials. These should all be basically review for you. Okay, so a monomial is a pure power of x. Right, that means it has coefficient 1. So namely, the monomials are 1, which is x to the 0, also x, x squared, x cubed, etc. Right, so x to any non-negative integer power. And let me just mention that sometimes people will allow coefficients on their monomials, but for us, we'll just call it a monomial if it's just a power of x and the coefficient is 1. Okay, and a polynomial, every polynomial is going to be just a linear combination of finitely many monomials. That's the thing to notice here. Every polynomial in x is a finite linear combination of monomials. Right, so now we're getting kind of vectory, kind of linear algebra-y. You take all these monomials, and you can scalar multiply by constants, by real numbers, and you can add them together, and you can build any polynomial that you want. Right? So again, let me just write this polynomial down again, just so we can look at something. Okay, so then once you've written a polynomial as a linear combination of monomials, then each of these summands is called a term. Right? So these things are called terms. This polynomial has 4 terms, which are just constants times monomials. I could say scalar multiples of monomials. Okay, and the constants here, these things are called coefficients. Again, none of this should be new. I just want to make sure that we have it all down. Right, the degree of a polynomial is the highest power of x that appears with a non-zero coefficient. And that makes sense because, again, we said that every polynomial is a finite linear combination of monomials. I'm not allowing infinite sums of monomials. That would be a power series, and that's not a polynomial. So the degree of a polynomial is the highest power of x that appears with non-zero coefficient. So in our example, of course, the highest power of x that appears is 5. So the degree of p of x is 5. Okay, the leading term is the term that has the highest degree. It's the term, term with highest degree. So the leading term of p of x is x to the fifth in our running example, and the leading coefficient is the coefficient on the leading term. So in our example, that's 1. Okay, and the point is that if I just tell you the coefficients of a polynomial, then it determines the polynomial. Assuming that I also tell you all of the zeros, right? So any polynomial is determined by its coefficients. And when you list the coefficients of a polynomial, you also list zeros where the term doesn't appear, right? So again, let me rewrite this polynomial for the third time, just have it on every slide. This polynomial has no x cubed term, right? It also has no x term. So you would say that the x cubed term occurs with coefficient 0, and the x term occurs with coefficient 0 as well. So when you give the coefficients of a polynomial, you also provide the 0 coefficients, at least up to the degree that you're at. Okay, also, it makes a lot of sense to actually list the coefficients from the constant term up, right? Because if I give you an arbitrary polynomial, it could go up to sort of any degree. It could go up to degree 5 or degree 10, but it always starts with constant degree, right? So it's bounded on one side. So usually we list coefficients from the smallest coefficient, from the constant term in increasing order, right? So we usually list coefficients of a polynomial in increasing order by degree. Right, so p of x has coefficients -10, 0, 8, 0, -20, 1. Again, I'm including the x term and the x cubed term, even though they sort of don't appear. They do appear, they just appear with coefficient 0. That's a scalar multiple times x, right? And now the thing to notice is if I hand you these coefficients, you know exactly what the polynomial is. So I can think of these coefficients as a vector, right? So we can represent our p of x by the vector -10, 0, 8, 0, -20, 1 in R6. If I gave you this vector, you would know exactly what degree 5 polynomial I was talking about, right? Okay, and in general, we'll use the following notation. So the general univariate polynomial over R of degree d is, we'll write it usually like, we'll use a's for our coefficients, and we'll label them by what degree they occur in. a1x plus a0, where each ai is a real number. Okay. Oh, and sorry. And AD is non-zero because I'm saying that this is of degree D. Right? Now, if you know the polynomial has degree D, then you can uniquely represent it by a vector in Rd plus 1 just by listing all the coefficients. Right? It is uniquely represented by the vector a0, a1 up through ad in Rd plus 1. That's sort of what we've developed so far. Okay, now that's okay if you're in a fixed degree, right? So if I want to consider all the polynomials of degree 5, I could just consider them as vectors in R6, right? In fact, if I want to consider all the polynomials of degree less than or equal to 5, I could consider them as vectors in R6. But once, if we're not in some fixed degree, if I'm allowing any degree that I want, then it's not clear what to take here for the length of your vector, right? If you're giving me vectors of length 6, but now I want to talk about degree 10 polynomial, I can't do it in terms of giving you 6 coefficients. I need to give you 11 coefficients, and there's no way to do that with vectors that look like this, right? So this is a new kind of vector space if you want to consider all possible polynomials, because you don't know what length the vectors have. There is no length, there's no fixed length that will work for every single polynomial. Okay, so this is our first example of an infinite dimensional vector space. Okay, so if you look at the set of all polynomials in the variable x with real coefficients is denoted R adjoin x. Okay, so like I just said, probably the way to read this is R adjoin x. You're taking R and you're adding the variable x. Okay, and the point is that we've known since, I don't know, elementary school or something, that if you take two polynomials and you add them, you get a polynomial. If you take two polynomials and you scalar multiply, you get another polynomial. And so this set of polynomials admits an addition and a scalar multiplication with really nice properties. In other words, they form a vector space. But it's a little bit different from all the other vector spaces that we've really thought about before in this class and in 308, in that it's infinite dimensional. There's no finite basis for this polynomial ring. The one possible basis is every monomial. But of course, there are infinitely many of those. Okay, so we know that we can add and scalar multiply. And scalar multiply polynomials. Right, just the way you've always done it. You add polynomials term by term, and you scalar multiply by scaling every single coefficient. And these things have nice properties. These two operations have nice properties. So this R adjoin x forms a vector space. There's also a zero polynomial. But as I said before, this polynomial vector space is a little bit different. What is a basis? Well, a basis should be a linearly independent spanning set. And the most common choice of basis, although there are many different choices of bases that have different applications, but one choice is called the monomial basis. It's, I think, the easiest one to get your head around to start. We'll call it B, and it's 1x, x squared, x cubed, x to the fourth, ... You should think about why this is a basis. Well, first of all, every polynomial you can write as a linear combination of these monomials. In other words, every vector in Rx you can write as a linear combination of these vectors. That means that they span. And then the 0 polynomial you could define to be 0 plus 0x plus 0x squared plus 0x cubed plus dot dot dot, right? And so the only way to get that as a linear combination of these basis vectors is by taking every coefficient to be 0. Okay, so this is our first example, and it's a very natural example of an infinite dimensional vector space. So this basis has infinite size. And the definition of dimension should be the number of vectors in a basis. And that means that the dimension of this vector space is not finite. It's an infinite dimensional vector space. Okay. But, sorry, I'm now realizing that I used wrong notation here, so you should go back and fix this, because it's the thing we're about to just define. Even though this big vector space is infinite dimensional, we can consider a bunch of smaller vector spaces living inside of it that are finite dimensional vector spaces. And as I said before, if you only want to consider polynomials of degree less than or equal to 5, then suddenly you do have a finite basis, and you can think of that as a finite dimensional vector space. And sometimes you know, oh, I only want to deal with quadratic polynomials, in which case that's the vector space that you want to work with. Okay, so if we restrict to considering polynomials of degree at most d, then the subset of polynomials is called or denoted Rx less than or equal to d. Okay, and again, you should check that this is a vector space. So this is a vector space. Why is that? Well, the 0 polynomial, technically, I guess you say, by definition, you say that the 0 polynomial has degree negative infinity, so it has degree less than or equal to d. If you add two polynomials of degree less than or equal to d, because you add term by term, you never pick up any higher degree stuff, right? So the result is a polynomial of degree less than or equal to d. Same thing, if you scalar multiply, you either have the same degree, or if you scalar multiply by 0, then you go to degree negative infinity. Regardless, you always end up with a polynomial of degree less than or equal to d. Scalar multiplying doesn't increase the degree of a polynomial. And so this is a vector subspace of R adjoint X, right? So maybe I'll say it that way. This is a vector subspace of R adjoint X. And it has a finite basis. Right, so I'll call the basis BD, and you just take all the polynomials up to degree d. And again, the dimension of a vector space should be the number of vectors in a basis. And so this vector space Rx less than or equal to d has dimension, you gotta be careful here, it's d plus 1, right? Because you have to have the constant polynomial 1 in order to get every polynomial. Okay. And so this is listed as a proposition. Everything that's on this slide is listed as a proposition. So this is technically proposition 7.1.2. Okay, and the thing to notice is that this polynomial vector space, consisting of polynomials of degree less than or equal to d, is kind of a familiar object, because you can identify every polynomial with a vector in Rd plus 1. Right, so using this thing that I wrote down a little bit too low. Every polynomial you can uniquely represent it by a vector in Rd plus 1, which means that this vector space of polynomials of degree less than or equal to d basically behaves exactly like Rd plus 1. In the language of mathematics, you would say that those two vector spaces are isomorphic. Right? So there's a bijection between this new vector space of polynomials and this old d plus 1 dimensional vector space rd plus 1. And the bijection, what you do is just what we did before. You send this polynomial, you map it to the vector a0, a1, a2, ad. Okay, and not only is this a bijection, it's actually a linear transformation. In other words, this map plays nicely with addition and scalar multiplication. So this is a linear transformation. And again, this is not a surprising result, right? The point is that when you add two polynomials, you add them term by term. When you add two vectors, you add them position by position. So the addition, you're doing the same thing, right? You're just adding them term by term on both sides. When you scalar multiply a polynomial, you scalar multiply into every single coefficient. So you just multiply every coefficient by the same scalar. When you scalar multiply a vector in rd plus 1, you just multiply the same scalar into the entire vector. So when you think of a polynomial as a sequence of coefficients, if you add them, it's just like you're adding the coefficient vectors. If you scale it, it's like you're scaling the coefficient vector. So this vector space behaves exactly like this vector space. Again, you would say that these are isomorphic vector spaces. Okay, and that is useful. Again, polynomials, maybe I should start the lecture with this. Polynomials are some of the most useful functions in mathematics, in applications of mathematics, because polynomials are very, very flexible, right? You can basically make almost any shape out of polynomials. On the other hand, their properties are super duper nice. They're defined everywhere. You can differentiate them. You know how to integrate them. And so representing something by polynomials or approximating something by polynomials is a really good way to understand, say, an arbitrary function. But now if you can also think of them as vectors, then you can suddenly apply linear algebra. So you can think about, for example, the differentiation function. That's a map from some vector space of polynomials to a vector space of polynomials. It ends up being a linear transformation because differentiation is a linear operator. And that means that you can represent it with a matrix, and suddenly you can use linear algebra to study that. Okay, so this is a useful identification. Sometimes we want to think about polynomials, sometimes we want to think about vectors, like regular old column vectors. And you can, because those are basically the same thing. But again, sometimes we want to consider all possible polynomials, right? This infinite dimensional vector space. And then it's not possible to think of these things as vectors because they don't have a fixed length. The most natural way to think about them are as polynomials. Now, a second ago, I very briefly said that you can make sort of any shape with polynomials. And that's the next thing that we want to talk about, the idea of polynomial interpolation, which means finding a polynomial that goes through a bunch of points, right? So this is polynomial interpolation. All right, so here the question, which we'll try to understand in terms of both polynomials and linear algebra. So given m points, I guess I should say, yeah, m values really, t1, t2 up through tm in R, is there a polynomial f of degree d that has values beta 1 up through beta m at the points t1 up through tm? Okay, I see why they're called points in the notes now. This is a very natural question, right? If I pick a bunch of points, t2 is here, t3 is here, and then I pick a bunch of values that I want to occur. Right, so here's beta 1, here's beta 2, Here's beta 3. I could ask, does there exist a quadratic polynomial that passes through these 3 points? I could ask, does there exist a degree 3 polynomial, a degree 4 polynomial? How many exist? And this is just a generalization of asking, like, is there a line going through these points? And of course, you know that there's not a line going through these points. But it turns out that there will be infinitely many degree 3 polynomials that go through these points. This is the question behind polynomial interpolation. I give you some points. Is there a polynomial that will fit these points? Okay, so mathematically, we want to know, or we want to find coefficients a naught up through ad, with, of course, ad being non-zero if you want it to be degree d, such that if you look at this polynomial, this is the polynomial that we're looking for, and you plug in the ti's in for x, then you get the beta i's, right? So f of ti equals, that's ad ti to the d plus a1 ti plus a naught equals beta I for each I. Again, very, very natural question. Like, as a good example, you have a bunch of data and you're wondering, is there a nice simple function that models my data? Or in fact, models it exactly. Is there an exact degree 3 polynomial through these points? Because then I could use that degree 3 polynomial to interpolate or extrapolate the value that I would expect at different values of t, right? And this is a very concrete, very actually easy to solve linear algebra problem, and polynomial problem, depending how you want to think about it. So here's the algorithm. So we can solve this problem, or maybe I'll say we can answer this question exactly. Okay, so remember, we want the polynomial, we want the coefficients of the polynomial. Right, so here, the ai are unknown. The x is a variable, the ai's are the unknowns. Okay, and then you want it to evaluate to beta I at ti. That means you can plug in m values into this polynomial. So what do you want? You want ad t1 to the d plus, let me leave off most of these. You want this to equal beta 1. You want ad t2 to the d plus a1 t2 plus a naught to equal beta 2, down to ad tm to the d plus a1 tm plus a naught to equal beta m. But hopefully you can recognize this as a system of linear equations in d plus 1 variables, where here the ai's are the unknowns, the ti's and the beta i's, you know them, right? you know what these points are. You're asking, does there exist a polynomial through them? That means you know the ti, you know the beta I. What you don't know is the ai's. Right, so this is a system. This is a linear system in d plus 1 variables, d plus 1 unknowns, a naught through ad. Okay, and of course, we've known how to solve systems like this since the first week of 308. What do? You put them into a matrix form, right? So we are looking for, again, the traditional way is to always write them with increasing degree. And you're going to want this to equal beta 1 through beta m, which means that this thing should be a m by d matrix, right? This will have m rows and d columns. And what represents this system up here? Well, you just take the coefficients in front of a1, sorry, a naught, a1, a2 up through ad. So this one is 1, t1, t1 squared, t1 to the d, 1, t2, t2 squared, t2 to the d, down to tm squared, tm to the d. As promised, sorry, I should have said it, it's an m by d plus 1 matrix, right? This one is m by d plus 1. This one's a vector in rd plus 1, and it spits out a vector in rm. Right, so let's call this matrix M. Let's call this vector B. And this vector that we're looking for, we're going to call F because it will determine our polynomial F. Okay, and this question of does there exist a polynomial of degree D that goes through these points is just exactly the same thing as saying, does this linear system have a solution? Or in fact, how many solutions does this linear system have? Of course, another extra comment is we also want to make sure that AD is non-zero, because otherwise it would be a polynomial of lesser degree. So you want to know if this has a solution where AD is non-zero. So does this system have a solution with AD not equal to 0? But of course, this is a question that you can just answer with Math 308. And we can even sort of understand how many solutions we expect there to be, right? If you have more columns than rows, then sometimes you can get infinitely many solutions. In fact, if there are solutions, there will be infinitely many solutions. What does that correspond to here? This is like if I increase the degree of the polynomial, it's more and more likely that I'll be able to fit m points, which makes a lot of sense, right? If I give you 3 points, you don't expect to be able to find a line that goes through these points because the degree is too low. Maybe there's a quadratic polynomial that goes through these points, but if I said, is there a degree 100 polynomial that goes through these points? The answer is definitely going to be, yeah, there should be infinitely many of them, actually. There should be tons of degree 100 polynomials that go through these points. Right, so that's reflected in the fact that as you up the degree, your matrix gets more columns without getting more rows. And again, if you add more points, it should become harder to have a polynomial that fits those points, right? If I give you 10 points and ask, is there a line that goes through all 10 points? The answer is only if the 10 points are really special, right? That's the same thing as having a lot of rows to your matrix. If you have a lot of rows but few columns, then the only kinds of points you can achieve are the ones that are in the column space of the matrix. Right? If you have 10 rows and 2 columns, right? It's like the only points that you can achieve are the ones that have on a 2-dimensional subspace of R10. Okay, now this matrix here has a really special form, right? It's just each row is 1, a number, the number squared, the number cubed, up to the number raised to the dth power. You can also think of it as the number to the 0th power, the number squared, etc. Matrices like this are called Vandermonde matrices and are extremely important and pop up all over the place. Their properties are really well studied. So matrices of the form M on the previous slide are called Vandermonde matrices. And you can just Wikipedia Vandermonde matrices, and you'll see that they're very well studied and very well understood. Okay, the second comment is one that we made already, which is if M is strictly less than D plus 1. In other words, if you have more columns than rows, then if there's a solution, there will be infinitely many solutions because you'd have a free variable. Then if MF equals B has a solution, it will have infinitely many solutions. On the other hand, if M is greater than D plus 1, then you may have no solutions. Of course, you may have solutions. Again, if you have 10 points, there might be a degree 1 polynomial that fits it if they happen to all lie on the same line, right? So there could be a solution. Taking these things together, though, the only way that you can potentially have a unique solution is if M equals D plus 1, so M is a square matrix, and the solution is unique if and only if M is invertible, right? We learned this in 308. And so there is a unique polynomial fitting the points if and only if M is a square invertible matrix, or just an invertible matrix. Square is implied there. So this means that M is equal to D plus 1. Okay, think about what this means in terms of, again, like this picture. M is D plus 1, so if you have 2 points, you want D to be 1. That says that the only chance to have a unique polynomial going through 2 points is if you say, I want a degree 1 polynomial. I want a line through these 2 points. And we know that that's true, right? Between any 2 points, there's a unique line. As long as the 2 points aren't on the same vertical line, then it wouldn't count as a function. That's a line, but it doesn't count as a polynomial function. There's no linear polynomial that gives you a vertical line. If you have 3 points, in general, you will have a unique quadratic polynomial going through those points, unless 2 of those points happen to be on the same vertical line as well. If you have 10 points, in general you'll have a unique degree 9 polynomial, as long as the points are not ever on the same vertical line. This is going to be the fact in general. Okay, this is, in fact, follows from properties of Vandermonde matrices. So this is a non-obvious fact, but if M is a square k by k Vandermonde matrix, then the determinant of M is equal to the following thing. Again, this is an extremely well-studied thing, but it's just the product of all of the ti minus tj's, basically. And so as long as none of your ti's are the same, in other words, as long as you don't ever take the same point on the x-axis, then the determinant will be non-zero, in which case it will be invertible, in which case you'll be able to find solutions in the square case, which is what I just said. If you have 10 points and none of them have the same x-coordinate, then there'll be a unique degree 9 polynomial fitting to them, because you'll get a square matrix with a non-zero determinant. It will be invertible. Okay, so really nothing this lecture has been new, I don't think. What is new is thinking about polynomials in terms of linear algebra, which is oftentimes how you want to actually think about polynomials when you actually want to work with them. And again, polynomials are super important in lots of applications, so it's very powerful to be able to do this. Okay, so there will be some problem set problems going further into polynomial interpolation. So you should let your intuition guide you as far as what you think should be true, but then you can show it using linear algebra, right? Okay. Now we move on to the next topic, which we won't finish today. We'll continue next lecture, I think, and that's solving a univariate polynomial equation and how it's related to linear algebra. Okay, now by solving, I really just mean finding the roots of a polynomial. So recall that if P is a polynomial, okay, now this is the grown-up mathematical notation to say that P is a polynomial. You say that it's an element of this R adjoint X, which is a vector space of all polynomials in one variable X, right? So if you have a polynomial, then the roots of P are the values of X such that P of X equals 0. Recall that we already saw in the fundamental theorem of algebra, which we didn't prove, but we saw that a degree d polynomial has exactly d roots as long as you include complex roots and you count with multiplicity. Right? So if the degree of p of x is equal to d, then by the fundamental theorem of algebra, p has exactly d roots over c, counting multiplicity. We also said that of course, the complex roots occur in conjugate pairs. So you could have 3 real roots, or you could have 1 real root and 2 complex roots. But when I say 3 real roots, I of course mean you could have all 3 being the same, right? So multiplicity 3, you could have all 3 being different, or you could have 2 that are the same and 1 that's different. So all these possibilities can actually happen. Okay, and so by solving a polynomial, you can always think about, okay, sorry. By solving a polynomial equation, what you really mean is solving some equation that looks like, x cubed minus 2x squared plus 5x equals 7. But you can always reduce to finding roots by just subtracting the constant over, right? So we mean finding values of x, making the equation true, making a polynomial equation true, but this is always the same thing as just finding roots of some polynomial. Right, so instead of solving this polynomial equation, I could instead just find the roots of this polynomial. That's the same thing as solving that polynomial equation, right? And we, I think, know at least at least 2 cases where we know how to solve polynomial equations. And that should be, we know how to solve polynomial equations if the polynomials are linear or quadratic. So we know how to solve if the polynomial is linear or quadratic. Right, of course, if it's a linear polynomial, that means it looks like just ax plus b. And the roots are, of course, there's only one root, so the root is negative b over a, as long as a is non-zero, but I said it was linear, so. And if q is quadratic, ax squared plus bx plus c, we hopefully all know the quadratic formula. The roots of this are given by negative b plus or minus root b squared minus 4ac over 2a, a thing that we learned a long time ago and never forgot. Okay, so solving low-degree polynomial equations, we already know how to do very easily, very algorithmically. We can just plug them into formulas. Okay, of course, this thing here in the quadratic formula, the part under the square root, is what determines the way that your roots are going to behave, right? If the thing underneath that square root is positive, then you're going to get 2 different real roots, right? Because it's a real number plus or minus a real number over 2a. If the thing underneath the radical is negative, you're going to get a conjugate pair of complex roots. That's where the imaginary part comes from. And if that thing under the square root is 0, then plus or minus 0 is the same thing. So you get a double root, right? So basically the entire behavior of your roots is determined by the thing underneath the radical. That thing is called the discriminant. So b squared minus 4ac is called the discriminant. Of the quadratic polynomial, q. Right, and if it's positive, then q has 2 distinct real roots. if it's 0, it has a double root, negative b over 2a just twice, and 3, if it's less than 0, then q has 2 complex roots, which are, of course, conjugates to one another. Okay, it turns out that there's also a formula for degree 3 polynomials, cubic polynomials. There exists a formula if in terms of just the coefficients and some basic algebraic operations. That formula is not one that you memorize because it's a little too complicated to memorize. If you have a degree 4 polynomial, a quartic in one variable, it turns out that there are actually formulas that will tell you the roots of a quartic. But you really don't want to memorize those because I don't think anybody really can memorize them. They're like several pages long. If you look on the internet, solutions to a cubic, solutions to a quartic, you'll see that formulas exist, but no one really memorizes them. It turns out that if you look at quintic polynomials, so polynomials of degree 5, there's a very deep result from an area of mathematics called Galois theory that says that there can be no general formula that finds all of the roots using only the coefficients and some basic algebraic operations: addition, subtraction, multiplication, division, and taking nth roots, any root that you want. Turns out that it's actually not possible to write down a formula. But we'll see how, which means that basically, since there's no formula, no linear algebra way will allow you to find all the roots of a degree 5 polynomial either, because if there were a method that would find all the roots exactly, then you could write down a formula for the roots of a degree 5 polynomial, which you cannot do. However, we'll see just how to think about solving a polynomial equation as a linear algebraic problem, just to see what the translation between polynomials and vectors can give us in this particular situation. And there are like linear algebra algorithms that will help you approximate roots of a polynomial that make use of this translation between polynomials and linear algebra. Okay, so again, nothing really new today. The new thing is thinking about polynomials versus vectors and being able to go between them. And as I said, you'll have some homework problems where hopefully this connection will be made stronger in your minds, because this is a very useful perspective in general.